Hi, about 5 years ago, I took this picture from the west side of Tucson looking east across the city and got treated to this wonderful mountain shadow with the Rincon Mountains in silhouette in the foreground. And in all the time I've been here in Tucson, I've never seen a mountain shadow being formed. I've never heard of one being formed, so this was really a unique situation. The photograph was January 7th, 2016, and it was about 7:20 a.m. I sent the picture to Les Cowley, who runs that wonderful atmospheric optics website. We discussed some of the general attributes that were present in the picture, but then I kind of dropped it, didn't have time, and recently I've taken it back up to try to explain just exactly what happened here. And you can see the Rincons in silhouette all the way down through the foothills. You can see that it's very clear to the far east, which would be important so that nothing would obstruct the sun from illuminating whatever needed to be illuminated to create this picture, as well as illuminating the underside of the clouds. A hint for what the cloud altitude might be is here at Mica Peak, which is the highest peak in the Rincons. The clouds look to be, I'm going to call it 200 meters below that peak. And so I have a hint of the altitude of this cloud deck, which we'll just try to use and see how well it works. The predominant shadow, S1 here, which is very vivid and striking, comes right over this plateau in the Rincons. And my first thought was, well, it's the plateau that's creating the shadow, but Les told me, given the distance, that that just wasn't possible. And I sort of tabled the whole effort at that point. But he also pointed out some other things, that there are really 4 shadows to be looking at. There's this main one, there's this S2 one, and then it looks as if there's another shadow here in S3, and then there's a S4 off to the southeast, which is something's casting a shadow into the haze at the ground level. So we got to try to explain all of these different aspects of this photo. Another clue is that about where all of the S1, S2, and S3 shadows end, that's pretty much where the sun stops illuminating the underside of the cloud. This video is going to be about my journey trying to explain all the details of this picture. I'm going to make heavy use of the really marvelous app, the photographer's Ephemeris, as well as the 3D version. I'm also going to build a stick model in MATLAB that will help illustrate what's happening. So let's review how a mountain shadow forms. You need an isolated mountain peak. You need a very low cloud deck. And you need the sun coming from behind, in this case kind of off to the side and behind. And it needs to be below the horizon. But it can't be very far below the horizon, because then you wouldn't be getting sunlight on the back of the mountain and onto the tops of the clouds. Maybe a degree, maybe a degree and a half, depending on what's behind. So the light from the sun hits the back of the mountain, which then casts a shadow which goes upward. And when that finally intersects the cloud deck, it forms the shadow from the mountain. So now if we change our view so that the sun is below the horizon, directly in back of the mountain, all right, you'll see that the sun hits the back of the mountain, and then the shadow gets thrown forward and upward until it finally hits the elevation where the cloud deck is, and then it creates the shadow. But you can see a feature of this, depending on the height of the clouds above the top of the mountain, is that there's a gap. before the shadow forms, because it has to travel towards you and upward for a while until it finally intersects that cloud deck. You can see a crop-in view of that central shadow from my picture that there is no gap along this plateau in the Rincon Mountains. That shadow goes all the way down and probably to the other, beyond the back of the plateau. So that's one clue that this shadow is not formed by that plateau, and instead it's just a happy coincidence. So now let's fire up the photo ephemeris. First thing to do is put the red pin on the observation site. So I'm zooming in to where I was on Ironwood Hill. There's West Ironwood Hill. It was about a mile west of Silver Bell, which is this street. Not quite to Shannon, which is this street. And I clicked the red pin and it'll put it in the page I'm looking at, or the area I'm looking at. And I was right about here. I've set the date for January 7th, 2016. I have the time set for 7:21 a.m. Now let's take a look. Well, we have the sunrise azimuth as this dark gold, and then we have the actual line to the sun as this very thin light gold line. Let's take a look at first interesting feature. It intersects, and that will be here. This is the Rincon Mountains. I'll just take a quick look here. Okay. This is the Rincon Mountains right here, and this is the Catalina Mountains. So we see that we have to identify that plateau. And I identified the plateau as this area right here. And it also has, if you go back to that picture, you'll see it has a cap on the left side of the plateau, and that is this cap. We'll move to Google, get a better look at it here. There we go. So there's the cap, and here is, it's one of these two coming out this way. Whichever one's the highest. I suspect it's this. This is the plateau that you see in silhouette. And I verified this feature with Tom, who knows the Rincons pretty well, and he agreed that it's this plateau. This is just west of this area here, which has the La Salvia picnic area. So, just for fun, let's turn on the geodetics, and let's put it right through the center. So we know we had the cap on the left side, and the shadow was centered pretty much on this ridge. And then the ridge drops off, which is what's here. So let's follow it out. And let's back off a little. So we're headed through the Rincons. And you can see that there's a nice low level here, so there's nothing obstructing. There's a low level in front. All that makes sense. And then we take it till we get to the first major feature here, which is the Dragoon Mountains. And it's a long range. And let's take a look. If we put the geodetic pin on the center of this feature, which is the high point is about here, I guess. Let's take a look. For some reason when I'm in Google Maps, it does not get the elevations. That's about 1,900 meters, 1.9 kilometers. And just for fun, let's take it back and see where it intersects that plateau. Remember, the red pin is where I was observing from. And sure enough, there's the cap. There's that plateau extending to the south, in silhouette that is. And that feature in the southern part of the Dragoons is centered right on this little island in the southern part of the Dragoons. But we do have a problem now. So we've got sunlight coming in at this angle at 7:21 a.m., flooding this whole area with light. This part of the Dragoons is 1.9 kilometers. This part of the Dragoons is about almost 1.9. Up here, it's 1.9. Here, it's about 1.9. And then up here, up Mount Glen, it's a little over 2 kilometers high. Now, this is a problem, because if I back off now, I've got light coming in on this thin gold angle, strafing across this whole area. I've got most of the features of the Dragoons are almost as high as that island. So it should be, if we just kind of draw some parallel lines here, the Dragoons, if they're responsible for this, should be making a huge shadow across that you can see above the Rincons, this whole range. And that appears to be a problem. Why would I just see the shadow from this mountain, which is centered over that little plateau? Why don't I see the entire shadow progressing at this angle over the whole Rincons? Something is up. But it's clear this piece of the Dragoons goes right through the center of that plateau there, which is exactly what was observed. So now I have to look at, we've got the sun coming up in the east. I have the Swiss Helm Mountains here, and I have the Chiricahua Mountains here. And then this is the Dragoons and then the Rincon. So as the sun comes up, it must shadow the Dragoons because of the Swiss Helm Mountains, which are high here, and the Chiricahuas, and leave this peak isolated. And if I continue to draw through that center island, you can see that the sun could get through and hit that peak because the Swiss Helms have come down into the foothills. I think this is the Leslie Canyon area. And then it makes its way through here at a pretty low elevation. And then the elevations start increasing in this direction. And then the Swiss Helm Mountains, this is the Chiricahuas. And then in the Swiss Helm Mountains, they start increasing here. And these are high. These are really high mountains, and these are pretty high, at least 2 kilometers. So let's take a look at what's happening using the 3D portion of the photographer's Ephemeris to see if that theory is right. So I'm going to swap the pins. I'll put this one in a little closer to that, and then I'll go into the sphere. So this is a really awesome feature of Photo Ephemeris 3D in that it shows the shadowing of the terrain features against other terrain features. So you can see if a mountain that's out to the east is shadowing another set of mountains to the west, which my theory from before was that that's happening here. And I'm going to move the timeline now. Okay, so here, all right. So I'm going to start with it a little later, and you can see the shadows coming from the Swiss Helm Mountains here. You can also see, let me go out, pretty big shadows from the Chiricahuas. Okay, and now I'm going backwards in time to where we have the first hints of sunrise, and I'm going to zoom in a little more on the dragoons here, and I'm going to move back to about 721. Now here, everything is illuminated on the dragoons, the island, that long ridge, and then this area where Glen Mountain is. And I'm at about 722. If I, oops, now I gotta go forward. Okay, and now you see right there at about 721, this peak in the island in the dragoons is hit by the sun, as well as the Glen Mountain area. This whole piece of the dragoons does not yet see sun, so the sun just strafes over them and lights up the clouds that I saw over the rincons. But here I get a shadow formed, and here I get a shadow formed, and probably another shadow formed there. And if you follow the sun angle out along here, that goes about right over Mica Peak, the Mount Glen area. And this one goes right over the plateau in the rincons. So this is exactly the geometry and lighting needed that takes and makes an isolated shadow as part of the dragoons and covers up the rest of the long chain. Now, if I move out just another couple minutes in time, you can see that now the sun is high enough that it's not getting shadowed so much by the lowlands of the Chiricahuas out here and by the Swiss Helms, and the Swiss Helms predominantly shadow this whole thing. So now you would see a massive shadow above the entire rincons, right? But the sun is too high, so you wouldn't see it at all. So we'll go back to 721. And there we are. We'll move in a little bit more. Whoop. And there we have the isolated peak being lit by the sun and the Glen Mountain area being lit by the sun. And then the sun comes up over this section of the dragoons and underlights the clouds that are above the rincons. So I think this is the exact condition that is needed to create what I saw. So now let's build a model in MATLAB and see if we can't verify some of the details of the features. This certainly gives us a qualitative understanding that, okay, we can now explain why there isn't one massive shadow from the dragoons going over the rincons, and instead we've got a couple isolated shadows. And if you trace these back, this is S1 from the picture, and this goes right over, pretty much over Mica Peak in the rincons, so that's S2. So we've got two shadows explained, but now we gotta try to make sure with a simple model that the angles here work and that the shadow forms about where it looks like it formed in the photograph. So these following slides are how I'm going to try to build a relatively simple model in MATLAB that will help verify that the qualitative aspects of how these shadows got formed actually work out at sort of the next level. So my idea is to draw an ideal sphere at sea level, which is this big, thick black line, and it doesn't look spherical because the distance and height scales are completely different. But I'll show later that it all looks right. It's just you have to live with it looking a little weird. And then here at 0, 0 is sea level under the observation point that I took the picture. Next thing to do is to draw a line whose top is where I was observing. So it's 733 meters above sea level, and that is noted. So everything is going to be worked relative to the ideal sphere at 0, 0. Then I draw a line along the horizon, 0 degrees, out to the east, just for reference. And then I've taken my guess at the cloud layer height as 200 meters below Mica Peak. And I had the clouds stop somewhere out, 100 kilometers out, because we know that the far east is clear from the photograph. And this looks like enough cloud layer drawn in to do the job. In order to work all these various features into the model, Les Cowley turned me on to something called the Haversine angle, which is really helpful. And the Haversine angle allows you to take 2 points, each where the latitude and longitude are known, and you can derive the angle of those 2 points from the center of the Earth and the great circle distance along the sphere. And basically, as I've computed these, I've actually verified them in TPE just to make sure my model is working correctly. So the first feature I've drawn in, I'm just drawing sticks in for the heights of these various things. This is the top of the plateau in the Rincons. And so I computed a Haversine angle and used that to determine where the sea level point was. And then I just drew it up, the height. And the height was measured using TPE and the local elevation tool. And then I drew a line from the observation point over the top of the plateau in the Rincons and extended it out to where the clouds meet. I know that the shadow has to at least start there. Otherwise, there'll be a gap between the Rincon Plateau and the where the shadow starts. It may indeed start to the right of that, which would still fill it in. In order to test my model, I did 2 ways. I used TPE to calculate the geodetic angle of the Rincon Peak from the observation point, and then drew the line using that angle, and it went through the line that I drew using the height of the Rincon and the Haversine angle. So that worked out pretty well. And the height above the horizon also confirms the geodetic angle that I measured in TPE. So far so good. I'm accounting for local elevation and the sag of the Earth properly. Next, I drew in the height of the Dragoon South Island top. That's that little section to the south that we know is aligned with the Rincon Plateau. Again, I used the Haversine angle. I used TPE to get the geodetic angle and the great circle distance, and they give the same results as the Haversine angle from the longitude and latitude between 0, 0 and where it was measured with TPE. And if you use the geodetic angle, you can calculate the height of this thing above the horizon point here where I was observing, and indeed I got the same number. You can hardly see it, but it does stick up over the horizon, and the numbers work out fine. So again, the model, the simple sag model with heights from the sea level works fine. I guess that's the way Mother Nature builds it anyway. Lastly, using TPE to draw the line from the observation point through the Rincon Peak Center, then through the Dragoon Island lit spot, that little spot that lit up, and I kept extending it to the east down into Leslie Canyon, and I drew the height in Leslie Canyon, or that area, in this last stick figure. And this would represent as seen from the Dragoon Island peak, if you were up there looking down, this would represent the angle that the sun would have to get at before you could light the top up roughly. Now I've got at least an angle from the Dragoon Island peak to the eastern horizon. And Haversine angles also allow me to put angles measured at any of these points into the equivalent angle being measured back at the observation point here. And that way I can look at local angles here and here and convert them into this coordinate system. I made the axis scales equal, so now the sphere looks proper, right? And here are the little, you can hardly see, there's the Rincon Peak, there's the Dragoon Island Peak, and there's the high point in the horizon from the Dragoons. And if you were to magnify in on these, you'd see that each of these little sticks is angled, even though in the magnified view it doesn't look like they're angled because it's a tiny angle, right? And this also shows you the very thin angles that all of this stuff is happening in relative to the ideal surface of the Earth. So now I've looked at the angle of the sun at this horizon point at the time 7:21. I've drawn that angle corrected for the Haversine angle into this coordinate system through the top of that horizon and then out to the Dragoon Island and then out to the cloud deck, which is above the Rincon Peak. This indeed confirms that at this time the sun is hitting the top of that island. Now I've drawn a second line parallel to this first one at the same sun angle so that it intersects the top of the Dragoon Island Peak. And I've drawn that to where it hits the cloud deck. And amazingly enough, it intersected with the line of sight from my observation point through the top of the Rincon Peak. So that means it fills, the shadow fills all the way down to the Rincon Peak. This angle here represents the shadow from this Dragoon Peak in the sky from the observation point. So it extends all the way down to the Rincon Peak line of sight, and then it goes up into the sky some distance, and then it stops, just like it did in the photograph. So that I was amazed when this turned out. And again, making the axis scales equal shows you this is all happening just in an extremely thin set of angles near the horizon. Okay, so let's wrap this up by going back to the original picture I took about 5.5 years ago. I can now explain all these different shadows. S1 we've spent a lot of effort on. That comes from an island at the very south of the Dragoon Mountains that's casting a shadow because it's lit up behind it. The spaces and sky lighting on either side of it are due to the sun actually getting over the Dragoons. In this case, it's here. Because the Swiss Helm Mountains and the lower Chiricahuas, which are east of the Dragoon Mountains, shadow this long section of the Dragoons. Light can go over the Swiss Helms and light up and underlight the clouds here. But then as you travel farther north, the lower Chiricahuas are not high enough to shadow Mount Glen at the northern part of the Dragoons. And it casts this shadow, I'm calling S3, in my opinion, here. And then light gets around it still farther to the north, and it does some lighting here. S2 comes from a shadow created by this local cloud on the Rincons. It appears to be a cloud that's of lower elevation than the cloud deck defined just under Mica Peak, and that's the cloud deck I've used in this whole analysis, but it appears to be lower than that, and it's local and hugging the mountains. And the sunlight, which has passed over that middle section of the dragoons, hits this cloud and casts a local shadow on the upper cloud deck above it. And it has that characteristic gap between the thing casting the shadow and the shadow actually hitting the clouds, which means it's a very localized phenomenon. So S2 comes from a shadow created by this low cloud that's hugging the eastern side of the rincons. S4, I'm going to kind of punt on this one. It's created by some low peak, kind of like these are, right down here, that has a flat enough horizon to the east that the sun is directly lighting it. It's bypassing all the local mountains, and it's casting a very shallow shadow because that sun is below the horizon here into the, what I'll call the local ground haze. And that's where that shadow comes from. I'm sure I could fire up TPD 3D and figure out exactly what is causing it, but I'm going to punt on it. And in the background, I've got the bearing to the shadow because this background is the Whetstone Mountains and Apache Peak here. So I've explained all 4 shadows on this photograph, and never before have I taken a landscape photograph that has required so much work to explain. I really appreciate the hints that Les Cowley gave me over 5 years ago in kind of what the general attributes of the scene were, and telling me about the Haversine angle, which was instrumental in making this work, and the folks at, was it Crooked Neck, that make TPE and TPE 3D. Wow, that's such an awesome tool, and without it I would have really had trouble explaining how there isn't just one giant shadow from the dragoons back here. So that was really helpful. Anyway, thanks for watching if you made it this far, and take care.